are produced using Mathematica, one of a number of software systems built to deal with mathematical tasks. But such packages are not just useful for creating beautiful images. They can also plot, manipulate, and solve complex mathematical formulas, both numerically and symbolically.
The idea of Mathematica is to make an environment for doing technical computations, but it's also to kind of package up this heritage of mathematical knowledge that's been developed over the past few thousand years. Sophisticated mathematics that was developed by Liouville and Galois, Cauchy, all these kinds of people, put it in a form where people can use that knowledge without necessarily knowing the details of how it all works inside.
Évariste Galois, Joseph Liouville, and Augustin Louis Cauchy all lived in Paris during the early 19th century. But the connection between these three goes beyond mere acquaintance and is tied up in a particular mathematical problem. It is a familiar fact that quadratic equations containing x-squared terms can be solved using a straightforward formula, giving two solutions. It is less well known that cubic equations, with x cubed as a highest term, can also be solved by a formula, this time more long-winded and giving three solutions. Quartics, x to the fourth terms, and four solutions. Again, there's a formula, this time fitting several screens. Yet the solution to the quintic, x to the 5, looks completely different. The reason why involves the relationship between our three French mathematicians and a story that involves politics, passion, and pistols. Most mathematical duels are fought with words, not pistols. But the mathematician who is commemorated here in the cemetery at Bourg-la-Reine, south of Paris, fought and lost a real one. Although Évariste Galois died at the age of 20 and left no material goods, his mathematical legacy is inestimable.
Évariste Galois was born in 1811, just after the Revolution. Until 12, I think that Galois stayed in his family, and he was very close with his mother, who taught him Latin and French and so on. And at 12, he arrived at the Collège Louis le Grand, which was very famous, and he began to study classical Latin, Greek, and so on, and the great authors. And at 15, he discovered mathematics. And really, he fell in love with mathematics. It was very, very important and surprising for him. He began to read the great mathematicians in their own texts, not in textbooks, really in the original memoir. And he was convinced that he was very gifted in mathematics.
Galois is not the only significant mathematician in our story. Augustin Louis Cauchy, deeply Catholic and a royalist, in a France where the revolution of 1789 was still within living memory, was the leading figure that Galois looked to for support for his mathematical work.
Cauchy est né en 1789. Il entre à l'école polytechnique en 1805 et il devient ingénieur. Il commence à faire des mathématiques à la fin du Premier Empire. Il s'impose tout de suite comme un grand mathématicien. Il est professeur à l'école polytechnique. En 1830, il quitte la France. Il part en exil.
It is perhaps inevitable that we will often find ourselves in graveyards. The protagonists in our story have all been dead for well over 100 years. Cauchy, who collected the title of Baron for his support for the royalist cause, lies buried here in Sceaux, now a commuter suburb of Paris. But graveyards can tell interesting stories. Next to Cauchy are the graves of his in-laws. His father-in-law, Marie-Jacques de Bure, was his publisher. Cauchy's wife, their daughter, lies buried over there. Cauchy was just one of the academics who made the Paris of his time the scientific and cultural center of Europe.
After the revolution created some institutions like the École Polytechnique, but there were also others, for instance, the future École Normale Supérieure. And in these institutions, you have the very important mathematicians who taught mathematics and also mathematical physics and so on. So really, it was the place where all Europe saw mathematics and looks for mathematics and so on. And all the important mathematicians of the whole Europe came to Paris to study, to meet people, and so on.
But meanwhile, what of Galois? In 1823, at the age of 12, as we have heard, he became a boarder here at the Lycée Louis-le-Grand in the center of Paris. The school had a double reputation, for its academic excellence and for the harshness of its regime. Galois would be here until he was 18. Two significant things happened during this period. As far as we can tell, it was here that he first gained his zest for mathematics, and it was here that he became political. He made one lifelong friend during this period, Auguste Chevalier. Though not a student at the Lycée, Chevalier was at the École Normale Supérieure. What they shared was a fervent Republican idealism.
I am sorry. You're Galois, aren't you?
Yes, Galois, Évariste Galois.
I've seen you.
You're at the École Supérieure, aren't you?
Chevalier. Auguste Chevalier. You'll be in trouble now. You've cut chapel. Do you think they spotted you?
I've got an excuse prepared. Anyway, I can't stand chapel.
Oh, nor me. All that military ritual. They say you don't do anything except mathematics. Is that true?
Of course not. I go to all my classes.
But not chapel.
Not when I think I can get away with it.
Desforges says that you're negligent, that you have strange fantasies.
I don't like his rhetoric classes. He's a simpleton.
So what do you like? Mathematics.
Of course. I want to be a mathematician. An original mathematician.
Desforges says you're original.
But he means it as an insult. He says I'm good. He told my mother I should be allowed to do mathematics and nothing else. Anyhow, what do you like?
You'd like them. I know you would.
Who? Like who?
The Saint-Simonians. There's a big group of us.
The political group. The socialists.
That's right. You'd find a spiritual home there. Oh, better than here. Nobody likes you here. They laugh at you.
What do you stand for?
It's you. I know it is. Christianity as a secular religion. And power to the scientists, not the priests.
Why would I care about that?
Well, the necessary conditions for progress consist of the elimination of poverty, the eradication of ignorance, public ownership, the abolition of social inequality. Come to our meetings. Read our newspaper.
The Globe.
Yes, the Globe. Here. Read it. Come with us. Join us.
Perhaps Galois' politicization was no surprise. He came from a Republican family. His father, Nicolas, once mayor of Bourg-la-Reine, had been hounded from office for his political beliefs and had subsequently committed suicide. His father's burial here had been interrupted by a politically inspired demonstration. witnessed by the 17-year-old Évariste. For the few remaining years of his life, radical politics was to be a driving force.
Nicolas Galois committed suicide in 1829. It was in a climate of political tension which began in France before the revolution of 1830. And the father of Évariste Galois was very liberal, and he really an odious campaign against him happened, and touched him very seriously with attacks, moral attacks, political attacks against himself. And I think that psychologically he didn't support this campaign.
But meanwhile, it was time for Évariste Galois to leave the Lycée Louis-le-Grand and move on to somewhere equally prestigious. A natural choice was here, at the École Polytechnique.
École Polytechnique was very prestigious, important, and he was really eager to enter in this école. But the examination was oral, and the question he received was considered by him very trivial. So he didn't take time to explain slowly to the examiner how to solve these questions. He gave directly the answer in a rough manner and so on, and he didn't understand after why his exceptional talent in mathematics haven't been discovered by the examiner.
No! No! No!
Tell me,
The man's a fool!
who was there?
Dinet. Dinet and Les Faubourgs de Fossey, buffoons, idiots, the pair of them.
What did they ask?
They asked about logarithms, something that simple. I was a fool. I should have come back with what de Fossey serves up in those dusty old schoolbooks he writes. No, I'm too clever. What do? I take a new route. I was brilliant. Brilliant! But the fools couldn't see it. I threw it away. Literally. I threw it at him. I literally threw it at him.
Through what, at who?
The blackboard duster. I don't know which one of them it was. I was just so mad at their stubbornness that I threw it at them. And when I threw it, I threw away my last chance. My second and last chance of getting into the École Polytechnique. What am I going to do now, dear friend?
I don't know. You have to go somewhere.
I could always join you at the École Normale Supérieure, I suppose.
Don't patronize me, Évariste. It's a good school.
And so soon after Cauchy.
It is now that Cauchy enters our story for the first time. In May of 1829, just before Galois' failure to enter the École Polytechnique, something unusual happened in the salle de séance of the Academy of Science. Cauchy had by now been an illustrious and prolific member of the Academy for 13 years. This room is essentially unchanged since that time. Some electrical equipment now, but still the ranks of desks for the academicians and the rostrum from which scientific papers were presented. On May 25th, 1829, Cauchy addressed the assembly.
Gentlemen, it is my honor to present to you a memoir of Évariste Galois entitled Algebraic Research.
So what was so unusual about this event? Since his election, there had been only one occasion on which Cauchy had presented the work of anyone other than himself. As a mathematician with so many publications of his own, he showed scant regard for the work of others. Galois' algebraic research paper was the first of two such memoirs to be presented to the Academy. 1 week later, Cauchy was again at the rostrum.
Gentlemen, my topic this week, again, a memoir of Monsieur Évariste Galois, is
Research into equations of prime degree. There was astonishment among those present. Cauchy had vouched for the quality of the work of some newcomer.
Very important works have to be presented to the Académie des Sciences, and they are presented through a member of this academy, and after, if they are accepted, they are published in the compte rendu. It's the review of the Academy of Science of Paris. And this is very important for the glory of a person.
Au début du 19e siècle, les principaux moyens de publication qui existent en France sont les publications de l'Académie des sciences, c'est-à-dire les mémoires que publie l'Académie des sciences, mémoires pour les académiciens eux-mêmes, et mémoires pour les savants qui sont extérieurs à l'Académie. Il y a aussi des journaux. Le plus important est le journal de l'École polytechnique. Et puis, il y a aussi un type de publication très important qui sont les manuels de mathématiques, parce que l'enseignement de mathématiques s'est considérablement développé au début du 19e siècle. Et donc, beaucoup de mathématiciens, y compris des mathématiciens importants, publient des traités de mathématiques, qui sont des ouvrages pédagogiques, mais qui ont aussi un intérêt scientifique.
Just being presented at a session of the Academy was not enough. The scientific worth of any paper was then subject to a rigorous process of review. In the case of Galois' memoir, the task fell eventually to Cauchy. Here was a busy man. This manuscript was destined to remain ignored until its contents were again brought to the forefront of mathematical consciousness in a very dramatic way.
Galois was preoccupied to solve one very old problem about the solvability of equations, mainly the quintic equations, which was not yet solved or studied, and also general equation of general degrees. Abel gave a first answer about the impossibility of solving the quintic equations. But Galois has more, I think, deeper ideas, because he invented the idea of group, to gather them in some groups and to study how a precise or given equation could or couldn't be solved. And he gave some criterions to answer to this question. And in fact, it's a very modern way to think to a problem, to give this problem in a general and abstract sense, and to give the different steps to study it.
There's an important distinction between solvability, what concerned Galois, and the mere existence of solutions. It was Gauss who had shown that the number of solutions of an equation is given by its degree, its highest power term. So this quadratic with x squared has two solutions, places where the graph crosses the x-axis. If the graph misses the axis, it has two complex solutions. If it just touches, two coincident solutions. In the same way, a cubic has three solutions, a quartic 4, a quintic 5, and so on. Not only do the solutions exist, but they can be found numerically. Galois was tackling a subtly different problem. Is there a formula for solving these equations, expressing solutions in terms of powers, square roots, cube roots, and so on?
Auguste, what are you doing, you idle politico, you?
Reading your mathematics, you hot-headed Republican.
And do you understand it?
No, but I'm trying.
What is it?
It's your work on the quintic equation. I can't see the problem. I certainly can't understand your writing.
The solution of equations, surely you understand that.
Of course. But that just makes the problem go away. If I have a second-degree equation, a quadratic, then I can solve it. I use my formula x equals minus b plus or minus and so on. It has two solutions.
Possibly coincident, possibly complex, but yes, it has two solutions.
My first degree equation, a linear equation, I can solve that by the simplest of algebra. It has one solution. Not complex, not coincident, just one solution.
Correct.
First degree, one solution. Second degree quadratic, two solutions. Possibly coincident, possibly complex. Third degree, the cubic, three solutions. Possibly coincident, possibly complex. With me so far, Évariste?
I'm just about keeping up, dear friend.
Fourth degree, the quartic. A question for you, Évariste. How many solutions? Possibly coincident, possibly complex?
Perhaps 4, Auguste?
Correct, mon ami. And now we come to this fifth degree equation, the quintic, on which you spend so much time. It has 5 solutions.
Possibly coincident, possibly complex.
Well, tell me, Évariste, what is the problem with this quintic? Gauss has shown us that any equation has as many solutions as its degree. 1, 2, 3, 4, and now 5, 6, 7, whatever.
Perfectly and totally correct.
So why are you and this Norwegian Abel so concerned with the quintic?
It's not the existence of a solution that is the problem. Gauss is correct. We can show quite simply that...
Simply?
That the nth degree equation has exactly n solutions. That is no problem. The question is whether these equations can be solved by human beings in an orderly manner. Whether there is a process that will give us the solutions in computable terms, in terms of radicals or roots, no less.
So it's not about whether the equations have solutions.
They always have solutions.
It's about whether we can find these solutions, to find a formula, in fact.
Correct. First degree, linear. Even you can solve that. Second degree, quadratic. A formula, a simple formula involving roots. Square roots.
Yes.
Third degree, cubic. Also a formula, not as simple, not as well known, also involving roots. Cube roots and square roots this time. Fourth degree, quartic. A formula, roots.
Go on.
Fifth degree, the famous quintic. I thought I had solved the problem, but there was a flaw. But now I believe I'm on the right track. That is the subject of my memoir to the Academy.
You solved the quintic using roots?
No, the quintic is not solvable using roots. But I'm after bigger game. I believe this is done. I wait, daily now, for news from Cauchy.
Galois' trust in Cauchy was misplaced. Whether it was disinterest, pressure of time, or more interesting work of his own, we have no idea. But Cauchy's refereeing of the two-part memoir that he had presented to the Academy on behalf of Galois never took place.
Cauchy semble avoir rencontré Galois donc en 1829 et il va accepter quelque chose qui finalement, semble-t-il, est assez exceptionnel. C'est une des seules fois qu'il l'a fait. Il va accepter de prendre le mémoire de ce jeune inconnu pour le présenter lui-même à l'Académie. Et puis il va se passer des choses finalement qu'on ne comprend pas, qu'on ne peut pas vraiment expliquer. Ce qui est sûr, c'est que ce mémoire va disparaître. On ne sait pas s'il a rendu ce mémoire à Galois, ce qui est tout à fait vraisemblable pour que Galois l'améliore parce qu'il va le présenter pour remporter un grand prix de mathématiques. Ou alors, peut-être que Cauchy l'a perdu. Ça reste, je dirais, une énigme.
In that document lay the foundations of mathematics that was to be significant then and remain significant today. The true importance of the Galois story is not in the excitement of duels and political maneuverings, but in how close we came to never discovering or understanding what Galois had done.
Il faut bien comprendre que pour Cauchy, Galois, il ne l'a à peine connu. Je dirais que c'était personne pour lui. C'était un tout petit jeune dont il a vu, je pense, le talent, mais bon, voilà. Et puis après, bon, il est passé à autre chose.
But now our story begins to accelerate. Galois was disillusioned by his treatment, but this was a time of political ferment, and he was in the thick of it. He was expelled from the École Normale for insulting his teachers, both academically and politically. He supported himself for a while by giving mathematics lessons, lessons which Chevalier attended. His Republican fervor increased. He grew disaffected with the non-violence of the Saint-Simonians and joined a more radical group. He ended up in jail for threatening the life of the king.
In fact, we knew that Galois, during his stay in jail, between July 31 and the beginning of 32, knew some lady, and he fell in love with her, and but we don't know exactly who she was.
Galois' lover may have been Stéphanie du Motel, the daughter of a Parisian doctor. Unhappy and destitute, his thoughts turned to his dead father, now re-established in the memories of the people of Bourg-la-Reine and again honored for his role as mayor. Galois had attempted suicide in prison. Now he once more contemplated ending his own life by taking part in a politically inspired duel. Of the many interpretations of what happened, the most plausible is that Galois, disaffected by his academic treatment and now disappointed in love, agreed to become a martyr to the Republican cause, contriving the duel as an excuse for an armed uprising. But we do not know. What we do know is that he completed this manuscript, now held here at the Bibliothèque de l'Institut de France in Paris, comprising some 7 folios which summarize the contents of the memoirs so far ignored by Cauchy, and added some new theorems and conjectures.
In the night before this event, he tried to gather all his mathematical works, all his ideas, and he spent all the night to write mathematical testament and a letter to Auguste Chevalier.
I do not have enough time, and my ideas are not sufficiently well developed in this area, which is enormous. Ask Jacobi and Gauss in public to give their opinions not on the truth, but on the importance of these theorems. What might have been? So much could have been different. I have failed so often. The École Polytechnique. Pity never. Hatred, that's all. Anyone who does not deeply feel this hatred for the present does not really love the future. Stephanie. Ah, the lovely Stephanie. The lost Stephanie. How can I console myself after the source of the greatest happiness known to man came to an end in only 1 month? Happiness and hope are now at an end, now surely consumed for the rest of my life. The rest of my life.
Galois was brought here dying to Cochin Hospital in Paris at 9:30 on the morning of May 30th, 1832. He had been wounded in the abdomen and would die in the early hours of the following day of peritonitis. We do not know who brought him here. One version speaks of a peasant on the way to market, another of a royalist officer, perhaps even his opponent. But some things we do know. A priest was sent for, and upon learning the identity of the patient, refused even to speak with him. His brother Alfred came, and we know that Galois remained faithful to the political story that his assailant had been a member of the royalist police. But what really happened must remain largely a matter of conjecture.
Auguste, dear friend, are you there? Are you there? Do not distress yourself. There is little time. There are things I must say. Be of good heart. I need you now, as I have never needed you. Take my scribblings. Promise me that you will bring them to the notice of the scientific world, to Jacobi, to Gauss, even to Cauchy. Promise me. Then it will be done. It will be over. Don't cry. I need all my courage to die at 20.
By 10 o'clock in the morning of May 31st, Ascension Day, the Republicans had the martyr they needed. Galois was buried here in the cemetery at Montparnasse in an unmarked communal grave. The burial was a farce. "3,000 people were present, ready to attack the police as soon as the coffin had been lowered into the grave. The National Guard was standing by. Then, even while the funeral orations were being delivered, news began to circulate of a more prestigious death. One of Napoleon's marshals, General Lamarck, was to be buried. There would be a large crowd, one even more politically and emotionally involved. The planned uprising would be more effective were it to be delayed by a trifle. Galois' interment came to a hasty, silent end. Politically, it had been completely pointless. But if the political story had come to an ignominious end, the mathematical story was just beginning. A new character enters our story now, Joseph Liouville. As chance would have it, he too lies here in Montparnasse. He is a link not only with Galois, but with the present-day components of our story, for his work too is an essential part of doing symbolic algebra on computers.
Liouville was educated at the École Polytechnique, where he later became a professor. He also later was a professor at the Collège de France and at the Faculté des Sciences. He wrote in total about 400 papers on different aspects of pure and applied mathematics, and founded a journal of the name Journal de Mathématiques Pure et Appliquée, also often called Liouville's Journal.
It was Liouville who finally interpreted and published Galois' memoir. But this was a process that was to take some 14 years. At first, Chevalier had strictly followed his friend's instructions in his last letter.
Ah, Monsieur Chevalier.
Good day, Monsieur Liouville. I trust that I am not hindering your work.
Not at all, sir, not at all. May I ask what brings you here?
I'm afraid that I intrude. I merely wished to inquire as to whether you felt able to offer an opinion yet as to the importance of the late Monsieur Galois' memoir.
The importance of that, there is no possible doubt. As to what it means, well, that is something again.
I do not understand you, sir. Have I trespassed on your goodwill by sending the papers for your consideration?
Not at all. I consider it an honor that you even thought of me in this connection.
I was advised so by your many admirers. After I had obeyed the precise terms of the letter.
To contact Gauss and Jacobi?
Quite so. After that, I heard nothing and sought for someone closer to hand. You come most highly recommended.
It is a small thing to be protective of young talent. I can assure you that it is not an imposition to peruse these works.
And you believe them important?
There is no doubt of that. The problem is that these results, both in the theory of equations and elliptic functions, are sketched in too concise a fashion. Even Poisson has admitted that he finds them incomprehensible.
But you believe that an understanding is possible?
Indeed. It is sufficient to devote a month or two to it without thinking of anything else.
It is so difficult.
Be of good heart. It has taken me longer than I had anticipated, but I am making progress. I intend to publish alongside it a commentary which will leave no doubt as to the reality and beauty, yes, indeed, the beauty of these results. I am making progress on many fronts. I'm already accustomed to using this new word, group. That is his term. And moreover, I have decided to offer a course of lectures to a number of selected colleagues, Bertrand, Sauret, among others.
Lectures on Galois' work?
Indeed. That is the normal way of coping with such advanced material.
Forgive me. I am myself a weak mathematician.
Whatever your low esteem of your abilities, Monsieur Chevalier, it is probable that history will record that the most significant document of these years was entrusted to your keeping.
You flatter me, sir, overmuch. Recall that these self-same results were once entrusted to Cauchy.
Ah, Cauchy. Brilliant as the man is, he has mathematical diarrhea. He would prefer to publish a single result in 10 different guises than to risk omitting to publish it once.
Although 20 years younger than Cauchy, Liouville had already begun to make his own mark on mathematics. The two men were both members of the prestigious Institut de France and were frequently thrown together.
Monsieur Cauchy. Monsieur Liouville. Are you here for the meeting?
Monsieur Cauchy, I have wanted to fall in with you. I wish to make a position clear.
Doubtless, doubtless. Are you still engaged with the manuscript of the Republican Galois?
Ah, yes, indeed, sir. And tiresome it can sometimes be. But I am concerned with another matter. The college?
The Collège de France?
I understand that you have applied for the position there.
Ah.
My own application was submitted before I heard that you too were a candidate. My own presumption mortifies me. I wrote at once to the board endorsing your candidature.
Hold.
It is clear to me that you are the superior candidate, indeed, surely the candidate of choice, and I have made my own view plain to the college.
Monsieur Liouville, please be still. I have news on the matter. The board have met and have decided...
Sir, may I be the first to congratulate you...
On a certain Monsieur Libri.
Libri?
Libri. I have heard that my political and religious positions have rendered me untenable. I have heard it said that they refuse to appoint the entire society of Jesuits to the chair of La Croix.
Sir, I am deeply humiliated as a man and a mathematician by what has taken place.
Even this interlude has its comic side. 7 years later, Libri fled his position, shortly ahead of a prosecution for the stealing of valuable books from the Collège library. The chair was vacant again. There was a chaotic election in which Liouville decided once again to stand at the last minute. Perhaps because of the political disfavor in which Cauchy found himself, it was Liouville who was elected. The contest was to lead to bad relations between the two men, but this is for the future. What is of interest for our story is why Liouville, though academically well-fitted, should have felt drawn to the editing of Galois' manuscript.
Politically, Liouville and Galois were both on the left of the political spectrum, whereas Cauchy was on the right. Cauchy was the supporter of the Bourbon monarchy, whereas Liouville and Galois were both Republicans. In another way, however, Cauchy and Galois were more similar in that they were almost fanatic believers in their political ideas, whereas Liouville himself, he said he was a firm believer in the Republican ideas, but he was moderate, he said, by temperament.
The moderate Liouville lived here in the Rue de Savoie, once the home of the mathematician Sophie Germain. In seeing Liouville simply as a character in Galois' story, we tend to underestimate the importance of Liouville himself. He began his career as a mathematical physicist, worked on electrodynamics and the theory of heat. He also proved the existence of a class of transcendental numbers. And most significantly for us, he tackled an area known as integration in finite terms. It is this aspect of his work which connects to our present-day story and the symbolic computer evaluation of indefinite integrals. Any reasonably well-behaved function can be integrated between limits, giving the area under the curve. The result is a number, and it can be found to any degree of accuracy using numerical methods. But how about doing it algebraically? To do that, you need an indefinite integral without limits, a primitive function that will differentiate to give the original function. This primitive function often exists, but the true problem, like the quintic, is whether this can be expressed in terms of more familiar functions. It was an attack on this subtler problem that Liouville left us. His results are now exploited on a daily basis, unseen by its users, inside the engines that power Mathematica and similar symbolic algebra systems. The key is the algorithm, or method, he developed to analyze a function and determine if its indefinite integral, its primitive, could be expressed in terms of well-understood functions. But Liouville's name lives on in other ways as well.
Liouville's mathematics, you can say, fall in several categories, at least two. One part of it immediately was absorbed in the mathematics of his time and therefore important to shape the mathematics of his time. One of these things, for example, his work on elliptic function theory or doubly periodic functions, was of that kind. Other parts of his work were so far ahead of his time, in a sense, that it wasn't picked up until some years later. For example, his work on Sturm-Liouville theory. It's a study of differential equations, but in a very qualitative manner that was very unusual at the time and wasn't really picked up until about 40 or 50 years later. Another idea is his work on differentiation of arbitrary order that hasn't really come into mainstream mathematics until this century, and the same applies to his work on integration in finite terms that, again, wasn't really picked up in the mainstream until it was of importance to computer algorithms.
Galois' work was finally published here in Liouville's journal. The journey to publication was not a simple one. Aside from the technicalities of typesetting and checking proofs, Galois' memoir was not capable of being simply transferred into print. For one thing, the original manuscript was hardly pristine in its appearance. For another, mathematics is not published like that. Although subsequent history has shown us the worth of Galois' writing, his scribbling, the content of the time was unknown and unfamiliar. But the Galois story is nearing its completion. Liouville did indeed lecture on the results around 1843, although we do not know precisely when or exactly who was in the audience.
At the end of a discussion involving so many algebraic equations, I want to excite the Academy by announcing that within the papers of Évariste Galois, I have found a solution which is both correct and profound of the following beautiful problem. Given an irreducible equation of prime degree, decide if it is solvable with the aid of radicals.
What Galois had done was to find a criterion for determining whether an equation of any degree could be solved by a formula involving radicals. His result, involving a group of permutations of the solutions of the equation, led to a new area of mathematics, group theory, with applications as diverse as quantum mechanics and error-correcting codes. What of Cauchy? He also worked on permutations, now part of group theory, but his major legacy is to analysis, in particular complex analysis, a subject that still strongly bears his mark. Moreover, he insisted on a high level of rigor in his papers and helped set standards for mathematical proof which continue to the present day. It may seem strange to look for the legacy of our three mathematicians in the office of a software company just outside Oxford. But this is the British branch of the American-based company Wolfram Research, whose founder was responsible for Mathematica. Their business is to turn mathematics into computer code. Although there are other mathematical software packages, such as Maple, MathCAD, and MATLAB, it is certainly one of the most comprehensive.
Mathematica is an enormously large software package, one of the largest software packages ever written, and nearly 1 million lines of code.
One of the objectives of Mathematica is, by being very clever about the way that Mathematica is designed from the point of view of the user, to make it possible for somebody who doesn't need to know all of the details of how it works inside to easily access the functionality that Mathematica has.
It's a very general software package which more or less handles all kinds of computations which come up in science and engineering, finance. It contains graphics, numerics, symbolics, and it contains a very nice interface which allows you, for instance, to use all kinds of Greek symbols, all kinds of other symbols. It has a nice palette interface which makes it also a useful instrument not only for scientific researchers but also for people at school.
So all of those ideas from Galois and Liouville, all these kinds of people that are in some cases quite difficult and sophisticated to understand, can all be sort of consumerized within Mathematica.
The selling of the software is a family business, with the British end run by Conrad Wolfram.
My brother is a physicist, and he was rather fed up with the kinds of tools that were available to him at the time, and so he started building his own software to do things.
One of my main motivations for building Mathematica is I wanted to have this thing myself. And conveniently enough, it's turned out that 1 million other people find it useful too, which is great. I built it from nothing. It's one of these cases where you start with nothing and you end up building the thing.
The thing is now a multi-million-dollar product that is available globally and in many languages, which by itself causes Wolfram Research problems in development and testing. Its applications are many and diverse, from the Olympic Velodrome to Wall Street, even in outer space. But do users of the system need to understand mathematics to run Mathematica?
The objective of the problem you need to understand. The exact mechanics you don't necessarily. You need to know the basic idea of what you're trying to do, but you don't need to know every step between your starting point and your end point.
The point is, once one's understood the principle of what one's trying to do, once one's been able to explain those principles to Mathematica, then you just let the computer go, and Mathematica can work out not just one example or two examples, but hundreds of examples and immensely complicated examples.
Something that calculator did for arithmetic. If you look back some decades, you'll find that many of the things that were being taught then were things about how to do particular pieces of numerical analysis, quickly, because you couldn't do them, like taking square roots and things you couldn't just do by pressing a button.
And a similar thing has now happened in a much wider range of mathematics, in symbolic calculation and in all of these other areas. So that's really what mathematics has done. It does not take away the need to understand mathematics. It does take away the need to know all the tricks associated with some of the mechanics of it.
What it's going to provide you with is just an answer. Here's your integral. It's not. It doesn't require. You have to understand you have to understand the concept of an integral to make use of this, but you don't have to understand all of the details, all of the mechanics of what's going on to be able to use it.
It's the ease of operation of software packages like Mathematica that makes them so popular. But there are those who question the reliability of computer manipulations.
The thing also that one realizes is that when one writes lots of the mathematics down that one does, one's actually not 100% clear about what one's writing down. At least I haven't been in various cases. And when you're putting this in a computer, you have to get it exactly straight.
But I find it rather charming, actually, when mathematicians ask me, how can they be sure that Mathematica gives the right answer? Because one can ask them, how can they be sure that the theorems they're using in their proof are actually correct? It's immeasurably harder to debug a theorem whose proof is written down on paper in a way that can just be read by humans than it is to debug what happens inside a computer program.
We tested to the best of all possible standards. This means we run overnight hundreds of thousands of tests. Before we release a version, we run millions of tests. We have all handbooks scanned with integrals, differential equations, which we check every day. But still, one can't completely exclude the possibility that a human makes an error or that some unexpected case happens in some algorithm and you sometimes get a wrong answer.
In fact, Mathematica now is one of the most complex pieces of software, complex application program that's ever been built. It's about 1 million lines of computer code, and it's something where, in fact, that computer code is some of the densest code that exists in any commercially available application, because it's something where one's having to use all of these algorithms that have been developed in the history of mathematics. It's not just code to move windows around on the screen, it's code to implement the ideas of Galois or Cauchy or whatever.
Implementing the ideas of Galois is easier said than done. After all, what he had shown was that the quintic is not generally solvable.
Anybody who's dealt with equations knows you can solve quadratics and cubics and quartic equations, but you can't solve quintics, or at least you can't solve them in terms of radicals. Well, I had heard from, over the years, various times, various obscure references to the fact that you could solve quintics if you went outside of the domain of radicals and included elliptic functions and other higher mathematical functions. And one of the things that we're proud of in Mathematica is having sort of assembled the world's most complete collection of these higher mathematical functions and having turned them into things that you can use as easily as square roots, so to speak.
The writing of software that can incorporate the whole of mathematics is enormously challenging, in part because mathematics is not always the rigorous language that we often think it is.
The traditional language of mathematics, the traditional symbolism of mathematics and so on, turns out, despite many aspects of precision in mathematics, to not be terribly precise. You have to know a lot of context to really know what all of those symbols in a mathematical formula mean. And so one of the challenges in building Mathematica was to develop a language that both humans could write and understand and computers could understand without ambiguity and with complete precision.
You have to get it exactly straight. You have to be sure you know what around parentheses means. You have to know what you mean by an equal sign, whether you mean it's an assignment or checking of an equality. All of those kinds of things you actually have to be very clear about.
The single greatest achievement of Mathematica is that sort of intellectual structure of the language that's been built in Mathematica. It's, I think, kind of like what Galois did in developing group theory. The original problem he was trying to solve of figuring out whether it was possible to express solutions to quintics in terms of radicals and so on is a fairly, at some level, practical problem, and is a problem that has not in and of itself been a critical problem in the history of mathematics or science. But the thing that he built in trying to work out the answer to that problem, namely group theory, was the seed into which a lot of extremely important things in mathematics and in a lot of other areas have grown.
Évariste Galois. Joseph Liouville. Augustin Louis Cauchy. Names familiar to mathematicians even today. All three would have been part of history in their own right, even had their paths never crossed in so dramatic a fashion. Cauchy died here at Sceaux at the age of 68. Liouville died at 73. Both men made lasting contributions to mathematics. It is useless to speculate as to what Galois might have done had he lived as long as they. But what is not a matter for speculation is the effect that the mathematics done 150 years ago has even today. Present-day mathematics students meet group theory at the start of the studies, and Galois theory, Évariste's enduring legacy, at the end.